Okay, thank you. I think I got the year wrong. It's 2019. I'm stuck in the past. Well, this was a talk from December, and I switched the date, but not the year. Okay, so this is based on work, several papers with various co-authors: Misha Belkin, Noah Golovich, Tengyang Liang, Ohad Shamir, who just gave a talk previously, Sasha Sibakov, and Shiyu Zhai. Let me say that I was particularly influenced in this work by the study of Misha Belkin and many conversations that we had on this topic. I apologize for the slow rendering. The Adobe Reader didn't want to display my PDF on at this resolution, so this will be a slow rendering process. Okay, so we've seen this type of tables that modern neural networks are heavily overparameterized, and in fact, it seems that the bigger you take the neural network, the better is your performance, and in particular, the number of parameters that you have in these neural networks is much higher than the number of data points, which on the CFAR is something like 60,000 or 50,000. So you've seen probably plots. This is from Neshabur and the co-authors. On MNIST or CFAR, the training error, as you increase the parameterization of the neural network, the training error, of course, drops, and at some point it just becomes 0. So this is not in time, but in terms of the width of the neural network. And the test error just keeps going down. So it becomes better and better as you take wider and wider neural networks. And this is something that happens across data sets, and it's something that is of interest. In this talk, I will not discuss the optimization side of the story. We've heard quite a bit about this, and we'll hear more. I'm interested in particular, in the red curves, in the out-of-sample performance. So why do these neural networks generalize, do something reasonable out of sample, even when the in-sample performance is essentially 0? So I will distinguish two regimes. I will distinguish the regime where the empirical loss on the data, empirical error, is close to the expected error, and I will call that the uniform convergence regime in my language. So this type of regime is when we have a good comparison of the empirical value and the expected value for the same neural network. And I will call this regime a memorization regime, because essentially, at some point, you start fitting the data exactly. You memorize the data, either in terms of the sign or in terms of the value. So I will refer to this regime as an interpolation regime, because in the least square sense, you would interpolate the data, and or memorization regime. So I'll use those two words interchangeably. So my talk will consist of two parts. One is on kind of this type of behavior, and another one is on this type of behavior. Let me just mention that it's unclear if the worst performance for smaller networks is due to the inability to computationally find a good minima. Maybe it exists, but we just cannot find it, or the model is not rich enough, right? So this question is, I think we have a poor understanding of it would involve some kind of assumption about the truth, an approximation error, and so forth. Let me also quickly mention that this is actually an old observation, that overparameterization leads to good performance. There are multiple papers in the 90s discussing this. This is just one of them by Lawrence et al. 97. As you increase the overparameterization of the neural network, the test error goes down. Okay, so here it's 364 times more parameters than the training points. Of course, these are at that time, it was a smaller type of problem, right? But this is just to recognize that the observation was already made decades ago, and the large margin theory came out of this observation in the late 90s. but it was, to some extent, too late because the interest in neural networks just died in the 90s. The winter came, and so it was somehow no one seemed to remember that anymore. Nowadays we have much larger data sets and many more new techniques, new interesting techniques. So we have to actually rush before the winter sets in, and no one will remember our results anymore. Okay, so the talk will consist of two parts. The first one is, as I said, the uniform convergence regime. The second one is the memorization regime. Let me start with this regime. So the setup is very standard. We have n IID data points from some unknown distribution P. And let's say it's a binary classification problem, so the labels are plus minus 1. The model will be denoted by f hat. This is the trained model, trained with the data. And we use sign of the trained model for prediction. Then we can write down the expected loss, which is the expected performance of our, or any function on the new couple xy drawn from the same distribution. So that's the expected performance. That's what we would like to be small, right? That's what we care about. Unfortunately, we don't have access to the distribution, so we can only compute empirical quantities. I will put hats on the empirical quantities. So this is the in-sample performance of a function f. In statistical learning, there are two basic approaches to guarantee something good about the out-of-sample performance of a hypothesis f hat n. There are many more, of course, but these are the two most prominent ones. And if all we know is that the algorithm outputs a hypothesis f hat n in some class f, or maybe in a collection of f's that is increasing according to some complexity, such as a sieve, then there are two standard approaches. The first one is to control the supremum of an empirical process. In other words, one tries to say, well, I don't know where f hat is. I don't know where my neural network is. So I will try to make sure that for all f in my class f, expected error minus the empirical error is smaller than something. Okay, so that's it's an approach that says, I really don't know which neural network I get. It's trained with the data, but let me try to uniformly control the differences between the expected and empirical errors. So the upper bound on this difference is known to be a tight upper bound within a factor of 2 is empirical Rademacher averages of the sign of f. So if f is a real valued class, and we're using sign of each function as a prediction, then the Rademacher averages of the sign of f give a tight upper bounds on this quantity. And then you get into Vapnik-Chervonenkis theory, which says that these Rademacher averages can be upper bounded by the VC dimension. And this is so-called parametric regime, because you end up having to consider the parameter of the sign of f, the dimension of the sign of f, and this dimension is the VC dimension, and for neural networks it's the number essentially related to the number of parameters. So as soon as the number of parameters in a neural network is larger than the data points, all of these bounds become vacuous. We all know this, and so we have to look for something else. So the second approach is to control the supremum, where you replace the empirical error of f with the empirical gamma margin error. So that's the proportion of mistakes that the function f makes within the margin gamma. So not only do you want to get all of them correct, but you want to get all the predictions correct with some margin gamma in terms of the real value. And now something magical happens, that you don't have anymore the Rademacher averages of the sign of f. Instead, you have the Rademacher averages of the f itself. So this is just a summary. I know this is standard for those who are from statistical learning, but this difference is quite significant. Here, you're stuck in this parametric regime where you have to consider the VC dimension. Here, you get unstuck, because you can now consider f as a class of real-valued functions. And this leads to upper bounds on this difference in terms of quantities that depend on norms of the functions in your class f or some other real-valued quantities, okay? Not just the sign patterns. So this leads to more like parametric regimes where, non-parametric regimes where you can have infinitely many parameters if you want. We don't care about the number of parameters. We care about some other notions of complexity of the class. So this is more precisely what the margin analysis gives you. This particular form is due to Kolchinsky-Panchenko, 2002. With a high probability for all functions in your class, and in particular for that neural network that you found after training, the out-of-sample error is upper bounded by the proportion of gamma margin mistakes plus 1 over gamma and the empirical averages of the class F, just as I mentioned before. Okay, so now the game is to minimize the margin mistakes, and that leads to the so-called large margin theory. I'm just recapping what was done in the early 2000s, late 90s. In particular, if you, let's say, you take a perceptron, these are linear separators, then suppose you take all the functions, all linear functions with norm bounded by, L2 norm bounded by B, then it's easy to show that this Rademacher averages of this class is just B over square root of n, and the number of parameters never appears in these bounds. Okay, so this is like a non-parametric regime. This bound has an a posteriori interpretation. So if it happens that you've obtained a neural network that has few margin mistakes, and you ensure that this is something that goes to 0 with n, then you've achieved some upper bound that's sensible. Okay. So what is the complexity for neural nets? We would like to define a notion of a ball in the space of neural networks, some kind of complexity ball in the space of neural networks. And it's unclear, and there is not a single correct notion, but so you can start with something like a sum of the Frobenius norms of the layers. I guess I didn't define the neural network, but it's clear. These are the weights in a fully connected neural network, and that's the sum of the Frobenius norms of the weights. And unfortunately, this has a bad property that it's not invariant to scaling. If you have ReLU, you would like to scale one layer by 100 and scale the next layer down by 100, nothing should change, but this one changes. So the next thing to try is to just take the product of the Frobenius norms, and you can take the product of all kinds of norms, and there are many results in this set of papers that I will not be discussing, but they're really, really nice and insightful. So let me just mention one result, which we got with Noah Golovich and Ohad Shamir, who just spoke in the morning. So what we can show is that for a class of neural networks with product of Frobenius norms bounded by B, Rademacher averages scale as B over n to the 1/4, or the minimum of this and B square root of the number of layers L. L is the number of layers, divided by square root of n. So at this point, this is as close to the perceptron as we can get, that B over square root of n for perceptron. This power 1/4 is something that we don't know how to fix, but perhaps this should be fixable by some smart person. Okay, so this is a few results in this memorization regime. And one can ask, why is this somehow insufficient for explaining the memorization regime? Why is this only somehow good for the uniform convergence regime? Well, if you look at this bound, remember that we got perfect fit to data, and you can look at the margin, and you can, for a reasonable margin, typically in neural networks, you can also say that this term is close to 0. The number of gamma margin mistakes is close to 0 for a reasonable gamma. One can say that this is small or 0, this is something that goes to 0, and this is something goes to 0. So we've got an upper bound that goes to 0, but we know that in real experiments we get something like a 20% error on CFAR, or 5% error, or 3% error on MNIST. So this is just somehow this is the wrong, or maybe it explains something, but it doesn't. It's not prescriptive. It doesn't really. It's unsatisfactory. Okay, so even though you get an upper bound that could be small, we shouldn't be striving to get the small, because we know that we shouldn't be getting something small on the left side. Okay, does that make sense? So this is only satisfactory for the uniform convergence regime when the empirical quantities are close to the expected quantities. And so what I would like to talk next about is the other regime. And for a while, it wasn't clear where to move from kind of this type of analysis, because it would inevitably lead you to comparison of empirical and expected quantities that leads you to this uniform convergence analysis. And kind of one realization is just that in machine learning, typically we're much more used to this type of bias variance decomposition, where you have an out-of-sample error of your trained model minus the base error. You decompose it into the difference between your error minus the best within some class, which might depend on the number of data points, plus the approximation error. So this estimation approximation error is what we teach in machine learning classes. But this inevitably leads you to uniform convergence results. You have to go through uniform convergence results to get a handle on the estimation error. In statistics, a different bias variance decomposition is studied, and this one, I'm going to only write it for square loss. So for square loss, you can write out this difference, which is kind of our objective. Again, f star is the base rule. In the case of square loss, this is just a regression function. You can write it as a variance and a bias term, and then you can analyze these without necessarily going into the questions of uniform convergence. So I think one of the kind of misnomers was, or erroneous conclusions was that we need to completely rethink some of the statistical learning because of this memorization regime. But in fact, it is true that in this decomposition, you have to go through uniform convergence. But it's not true for the second one. So that's the approach that we will take. OK, so the memorization regime. So now I will talk about the regime where you perfectly fit the data, and you still do well out of sample. And you can do very simple experiments. You take MNIST. You designate one of the digits as a 1, another digit as a -1. And then you just do kernel ridge regression. What I'm plotting here is what happens to the out-of-sample error for kernel ridge regression as you decrease the regularization parameter in the kernel ridge regression. And it just gets better and better and better, and the best performance is actually achieved at the 0 point. So at 0, there is no regularization, and somehow you are perfectly fitting the data, yet you do well out of sample. And indeed, this is not an isolated phenomenon. This was noted by these two papers, Understanding Deep Learning Requires Rethinking Generalization, and the second one, which was very influential, is to understand deep learning, we need to understand kernel learning. Especially the second paper did a lot of experiments with kernels and showed that some of the strange things that we observe with deep neural networks is already present in the kernel space. So this was an impetus for us to study kernel methods and try to answer, or try to at least address some of these questions about memorization in the context of kernel learning. So then we started thinking, can a learning method be successful if it memorizes the training data, period? Because in machine learning classes, we typically say that you should not fit the data exactly. And this is the mantra that, at least on the theoretical side, both in statistics and machine learning, we preach that. And that leads to a question of overfitting. So what is overfitting? And I gave this talk a couple of months ago in the ML colloquium here, so I apologize if you've suffered through that. So what is overfitting? Is it fitting the data too well? Or is it that the model is too complex? So these are different notions. Oftentimes, it's not clear what people mean when they say the model is overfit. And it turns out that these two notions, fitting the data too well or the model being too complex, these are two distinct notions. So as you will see, I will give examples where one can perfectly fit the data, memorize the data, and yet perform well out of sample. And that has nothing to do with model being too complex or not too complex. It's an orthogonal dimension of the problem. Okay. So the key, if there is something to take out of this talk, is that we should not conflate these, and we should be very careful about what we mean by overfitting. Again, if you look at the Wikipedia page, first it talks about an overfitted model as a statistical model that contains more parameters than justified by the data, whatever that means. But then goes on and says overfitting occurs when the model begins to memorize training data. So clearly, there is this conflation of whether overfitting means that you're fitting the data too well or whether the model is too complex. And these are separate things. And this is not just because someone wrote that Wikipedia page. You look at standard yellow books, such as this. Here, this one is less reasonable than that one because this may lead to fitting the data too well. It may lead to a function which interpolates the data, and hence it's not a reasonable estimate. So here's another one from a kind of a classical book by Hasty, Tipchirani, and Friedman. There is this bias variance trade-off curve, and there is this training sample curve. This is the kind of the sweet spot where you want to be. Of course, you don't know this curve, so you only see this curve. But the assumption here is that if you're here, if the fit to data is too good, then you must be in the overfitted regime. That you must be in the place where the model is too complex. And of course, here it says the model adapts itself too closely to the training data and will not generalize well. This is another snippet from the same book. A model with zero training error is overfit to the training data and will typically generalize poorly. It's good that they put that typically, because it seems like in most examples, actually, it's not true. So and this is also the same thing happens with AdaBoost and the regression trees and so forth. This is a snippet from Weiner from Penn et al. 2017. Indeed, the common law in statistical learning suggests that perfectly fitting the training data must inevitably lead to overfitting. And this aversion is built into the DNA of a statistician who has been trained to believe axiomatically that data can be decomposed in signal and noise. And then he goes on at the end here to say that the computer scientist has no dogmatic aversion to interpolating the data. Just don't care. Okay, so this is the path in terms of kind of a research path that we've tried to take. We started from, okay, so just knowing that you fit the data, that you've minimized the empirical fit to data is not enough, right? Because that somehow leads you to this thinking about comparison of empirical and expected quantities, and you don't get anything out of that. And so what we started to do is to ask whether we can explain the memorization regime first in the local kernel methods. Then we asked whether we can do it for global kernel methods. And then the kind of the end point would be, of course, to get to neural networks due to this recent connection between the kernels and neural networks that we've heard yesterday about. We'll hear more later in these few days. So let me start with the first example, and this is a relatively simple example where we have a closed form solution for the estimator. Now, okay, let me say this. It's obvious that you can always take a good estimator and redefine it at a finite number of points. Out of sample, nothing will change unless you get those points again in the training. So, of course, the answer is yes. Fit to data doesn't tell you anything, right? Because I can always come up with this weird estimator. But that's not the point. Somehow, the point is to see how much can we push memorization in natural memorization analysis in natural setups, such as Nadaraya-Watson estimator or reproducing kernel Hilbert spaces or neural networks, right? So that's the idea. So for the classical Nadaraya-Watson estimator, it has this closed form. So it's linear in terms of the yi, and then there are weights. And the weights tell you how much weight you put on this yi according to the distance in the x space. So for points close by, you assign a lot of weights to those yi's, and for the points that are far away, you don't care. So here we're going to assume that the model is f star, and it's smooth, and the data are generated in this way. Yi is equal to f star of xi plus noise. So the distance, this distance is given by a kernel. We take a kernel, which is just a function from Rd to R, and we define this notation k sub h with the bandwidth h to be just a rescaling. It's just a rescaling of the problem. And now these are the typical kernels that people take in non-parametric statistics. You observe that what controls fit to data is just the height of the kernel at 0. Why? Well, because here you want to see whether the kernel, whether the solution reproduces the value as yi when you plug in xi, and that is given by the kernel value at 0 relative to the heights at other points. So clearly, if you take the kernel to be going to infinity at 0, to be singular at 0, or cap it at some height tau, then you're approaching this overfitted regime. You're approaching the memorization regime. This was already observed in 1998 by Devroy et al. They looked at a kernel which is 1 over the norm to the power d for some specific value of d, and they show that it's a consistent estimator without any rates, and no rates are possible. And then they also show this weird property that it converges nowhere. So it's consistent, but it converges nowhere point-wise. And the problem is somehow the kernel is too global. It averages too many things. These tails of this 1 over x average too many things. And so we fix this problem by truncating the kernel. So we take, again, 1 over x to the power a, and then truncate it to be a unit ball. And the informal theorem, which I will just summarize, is that if you choose the bandwidth h in the right way, then the estimator has the optimal rates, which are classical in the statistics literature, under the assumption that beta star is that f star is beta holder. So here we have an example of an interpolating estimator. And in fact, we can control the amount of interpolation, whether it actually interpolates or gets close to being interpolating. And yet it's optimal. And these are two orthogonal notions. This is just a proof of concept that fit to data need not have anything to do with out-of-sample performance, which is probably obvious to many of you. OK, so the So shrinkage always pulls away from the data. And whether there's a connection between this, no, I think they're different. So shrinkage are global estimators. This one is like a local rule.
Well, if you do some linear shrinkage in Fourier domain, then you get the curve, basically.
Yeah. No. OK, so I think the more interesting one and the one that gets us a bit closer to the neural networks along this path is kernel ridgeless regression. So the next thing we wanted to see is what can explain possibly the good performance out of sample of regularized least squares when you send this regularization parameter to 0. So let me remind you that kernel ridge regression is defined as a solution of this problem where you fit the data with square loss and penalize the solution by the norm in that space of reproducing kernel Hilbert space corresponding to some kernel K. When I say lambda is equal to 0 solution, there are lots of solutions that pass through the data. And so when I say lambda equals to 0, we will choose the minimal norm solution to this problem. Many papers already point out that the peculiarity of good generalization in the overfitting regime or in the memorization regime is already exhibited by this problem. So we study mean norm interpolation. I will just refer to that as a minimal norm interpolation. That's the limit when lambda goes to 0. It's the minimal norm subject to fitting the data. So among all the solutions that you can have, what is the one that has the smallest norm in the reproducing kernel Hilbert space? And note that this is a solution, the minimal norm solution is a solution to which gradient descent or SGD converges if it starts with 0. So the message that I would like to convey is we've got some result that shows that geometric properties of the data plus high dimensionality of the data plus the curvature of the kernel function can yield a good generalization for the interpolated solution, even though fit to data is exact. So by the representative theorem, you can write down the minimal norm interpolant in this form. So Kx, capital X. So capital X is going to be the matrix of the data. And the K of little x, capital X, is the vector of Kx, x1, Kx, x2, Kx, xn. Okay, that's the vector. And Kx, x, this matrix, is a matrix of Kxi, xj. Okay? And that's the inverse times the vector of y's. This is the closed form solution. It's very similar to what we had before in terms of the just in terms of being explicit and being linear in y's, right? This is just a sum over y's with some weights. But the difficulty here is that the inverse aggregates these y's in a strange way, right? So it can say, oh, that data point is very important to me, and I will put all the weight there. So it doesn't have a priori this locality that is enforced in the local Nadaraya-Watson method. Okay? So it's clear that to study this closed form estimator, we need to understand the random matrix that's we're inverting. And let me first introduce a quantity, which is the effective dimension. The effective dimension of the covariance matrix XX transpose, let's just assume that it's centered. We're going to sum over all the eigenvalues and look at the eigenvalue of the covariance matrix, sample covariance matrix, divided by gamma plus the eigenvalue and then square it. Okay? So this is the effective dimension that comes into play in our analysis. And you can compare it to the effective dimension when you do regularized least squares. So this is typically treated as a low-pass filter, where that parameter lambda that we regularize with just tempers the bad eigenvalues, right? The small eigenvalues that can blow up the estimator. So the result that we obtained, and this is not a full answer to the story, but just a first step in that direction, is that under a bunch of assumptions which are not nice, so I would like to get rid of them, with certain probability, the generalization error is upper bounded by this intrinsic, the actual dimensionality of the data set, divided by d, and then there is a spectral norm of the covariance matrix, and then there is another term. And so, okay, maybe I don't have time to go through the details, but essentially, if you have a fast decay of eigenvalues of the covariance matrix and the fast decay of eigenvalues of the empirical kernel matrix, then this can yield something that's small. So that's at least a way to bring in the data and compute something on the data and see if that's a small number. And we've computed these quantities on the MNIST and some other data sets, and indeed the decay of the eigenvalues is very fast. Now, the key assumption here, one of the assumptions, just a second, one of the key assumptions here is that this is only true, that's assumption A1, only true in the scaling regime when the dimension of the data, the input dimension of the data, is something like n, the number of data points, up to a constant. And that's currently the limitation of this type of approach. So it only works in the high dimensional regime and doesn't work in the low dimensional regime. Yes?
So it looks like this bound scales with a lot of the smoothness properties of the estimator?
You mean the second part? This one?
Just the whole thing, it looks like it scales with
of the estimator.
very smoothness properties.
So what do you mean by it scales with the smoothness property?
If this is large, then Lipschitz constant, the estimator will also be large.
If this is large, just the first part or the whole thing? If it's large, then the Lipschitz constant will be large. I don't know.
Because the thing I'm trying to figure out is how adversarial examples they would play in this, because a lot of the estimators we're talking about are giving us smooth functions. So of course, neural nets can generalize very well, but they have very bad adversarial examples, which means their Lipschitz constant is very bad, but they generalize well. So that's one part of the story I'm having trouble merging with your story, where for a lot of these kernel estimators, the tester corresponds sort of to the Lipschitz constant and the adversarial.
Yes, so I think there is nothing that doesn't allow this to be, even if this is small, I think you can still have very large Lipschitz constant for the estimator. I think that it doesn't preclude that. We can maybe discuss it offline. Okay, so let's see, I have a few minutes. Let me just sketch how the proof goes is by extending a result of El-Karawi from 2010, which essentially described the structure of the random kernel matrices as being close to a linear kernel plus an identity, a scale of identity. And this gamma is what gives you the implicit regularization of this interpolated solution. Okay, let me go on. Okay, so yes.
If I go back to this, it seems that if I start regularizing, if I add a lambda times identity, I only increase the lambda. I only increase the gamma, which would only make me a better bound, right?
Yes, yeah.
This result does not tell me that I actually had an incentive to actually.
Yeah, it says nothing about which one does better, the regularized solution or non-regularized. It only gives some insight about why would this even work if you don't regularize. That's correct. Right. I should say that when one looks at this result, one says, oh, this just means that the solution is the same as the one you obtain by actually regularizing. And that's not quite true. So the solution that you obtain when you regularize does not pass through the data. If you just take the linear kernel and you do kernel ridge regression, in the experiments you do terribly and you don't pass through the data, you don't memorize. And this is just the analysis step. Okay? So this does not mean that linear kernel with regularization will work just as well, and it doesn't. So this is just the analysis step. Is that clear? Okay. Yeah, there are lots of assumptions which I don't like, and it would be nice to get rid of them. So this is work by Shiyu, who is somewhere there. So we looked at the Laplace kernel, which is just without the square, just the norm with some width sigma. And we wanted to see if interpolation with Laplace kernel is still okay in low dimensions. And what we showed is that it's actually not okay in low dimensions. So there is a lower bound that says that for low dimensions, for a constant dimension, with high probability, the generalization error is lower bounded by a constant. So if you think of the usual picture in 1D, where you interpolate the data points, and that's a bad solution, in low dimension, this is actually the right picture to have in mind. And in high dimension, something else happens. Points are spread out, and so it becomes okay to interpolate. But in low dimension, it's not okay to interpolate these data points. So the proof essentially looks at two possibilities. One is where you observe a function f star in noise, and you create a interpolated solution f hat. Because of this constant noise, you're paying L2 error here, and so that gives a lower bound in one of the regimes. And in the other regime, you are the sigma is too small, and then it just comes down to 0 too quickly, and so you're paying here and here. So that gives the second part of the lower bound. And a lot of work goes into showing that these two can be glued together, and this is work by Shiyu, that they can be glued together. And so the result is that there is no way to set the bandwidth, even after you look at the data, such that the interpolation with a Laplace kernel will succeed. So it is inherently good properties of interpolation with a kernel, at least with Laplace kernel, is inherently a high-dimensional phenomenon. Okay, so I should probably conclude here. So we take this path where we started with analyzing memorization and generalization properties of memorization for these local kernel methods. Then we move to these global kernel methods when there is this kernel matrix inverse that we have to deal with. And now there is a connection using the tangent, the effective tangent when the width is large, so that we can go to neural networks and try to analyze that. Okay, thank you.
So we have time for one or two questions.
So if we talk about learning with, say, Gaussian curves, when you make the width very small, so if I'm not mistaken, if you find the minimum norm interpolating solution as width goes to 0, you would basically converge to something like one nearest neighbor. And for one nearest neighbor, we have generalization guarantees that have nothing to do with uniform convergence. So in what sense do you consider this an unsatisfactory explanation for explaining the results you showed earlier, about how to make the width small and you still generalize?
You make this, so the lower bound part or the upper bound part?
Maybe it works just because you become something like one nearest neighbor, which is often a good predictor.
But one nearest neighbor works very badly in any example that you take. So, I mean, it has this property of being at most twice the base, but if the base is 10... Sure.
Any other questions?
So I'm sorry to throw that on you. It's a bit of a reflection of an identity crisis. But so everything that you're mentioning here is really about data interpolation is not good in the standard statistical learning model where I actually don't know what y is. I'm trying to learn a conditional expectation of y given x. But if I think about all MNIST and CFAR and everything, there's no noise whatsoever, right? You tell me this is, I don't know, a whippet dog, it is a whippet dog. Everything is perfectly classified. There's actually no real, like, at least in those classification problems, so maybe you're thinking about regression problems, but in those classification problems, I don't think there's actually that much room for classification error.
I don't know. I think this is where if you talk to one person, they say there is lots of noise. In CFAR, for instance, it's labeled by
someone, and I don't know. We can debate this.
Well, dog expert.
We can also check, but yeah, we can also debate. I think there is a little bit of noise. I don't know. Shibani? Yeah, so we don't have to debate. We actually did find some misclassified things. It's unclear how big of a fraction of the data set it is actually. Do you have any?
So people at Google actually looked at the SQL data set and they saw a lot of overlaps and some misstable examples, but I don't remember how much.
Yeah. We also know that there's a human that labeled the entire set.
Yeah.
And they got like 94%. There's a guy that went through and labeled the whole thing. He got 94%.
I see. Yeah. So, yeah. Well, honestly, for me, Safari is completely adversarial. I just cannot see what these pictures show. I will get 10% probably. So anyway, but there is some noise.
I think that it doesn't matter if there's noise, inherent label noise or not. I mean, the point is we cannot get in many places where we cannot get anywhere close to 0% test error, 0% generalization error. Is still the best method to do that is the 0% training error. Right? So I mean, even if you have something like 15% accuracy in some multi-class problem, then you still train to 100% accuracy or very close to 100%. And so it's, I didn't start talking about MNIST. I think it's very clear that in many cases and I don't care if that gap, that 85% error is because of noise or just because our class is not rich enough. It still doesn't, it's not something we can.
If you were just doing the classical thing of univariate interpolation, say you got a number of points that are on a line plus noise, and you were trying to find the minimum noise, the minimum non-polynomial that fits them without any bound on the degree. Would you get something that is basically the linear polynomial plus something of infinitesimally small norm that just fixes it for these particular points?
If you solve the minimal norm with a polynomial kernel, or is that?
So you had no bounded degree, just wanted minimum norm, and you just had points that were really from a line, but there's some noise, so that you get something of a very, very large degree that is really small.
Yeah,
that just fixes the data point plus the line.
I don't know. In the local, that's what you get. In the local, the first one, that's what you get. You get these blips. And that's clear. With the global, I don't know. Yeah, that needs to be worked out. It's essentially, you have to talk about the random X generation and how this kernel matrix behaves if the X's are sampled randomly.
Okay, so I think that's the time for the lunch break, so we can all debate different things. We'll meet again at 2 p.m. Thanks.